Hello everyone, in this video we're going to talk about how elements heavier than iron arise in the universe. They're all around us and inside of us, and about half of their abundance originates from extremely violent cosmic explosions. But how does this happen? For a long time, scientists had only a basic idea about the synthesis of these elements, but that changed recently when astronomers observed heavy element synthesis in action for the first time. It all starts with a massive star that dies in a spectacular explosion, giving rise to a neutron star, a strange and dense object that can be the size of a city. This neutron star may have cooled in space, but it's usually in a binary system with other neutron stars. And in a dance that lasts millennia, these stars spiral towards each other, and tidal forces begin to tear them apart, flinging neutron-rich matter into space at speeds close to 1/3 the speed of light. When they finally merge, a cosmic explosion occurs that sends ripples through spacetime and triggers cosmic fireworks across the electromagnetic spectrum. This explosion is so powerful that it can create heavy elements like gold, silver, platinum, and many others. These elements are flung into space and eventually end up reaching Earth and other worlds. After 3.7 billion years of evolution on our planet, these elements have become essential to our bodies and our lives. For example, iodine is a component of the hormones we need to control brain development and regulate metabolism. Gallium is essential to the chips in our smartphones and laptop screens. So, the next time you look at the stars, remember that they are responsible for many of the elements that made life possible on our planet. And who knows, maybe one day we can use these cosmic explosions to create new materials and revolutionary technologies. The universe is full of fascinating and exciting mysteries, and we are only beginning to unravel them. Imagine looking up at the sky and witnessing a cosmic cataclysm that occurred 130 million light-years away. That's what happened when gravitational waves began to propagate through spacetime and cross a vast expanse of the cosmos until they reached Earth. At that time, our planet was home to the dinosaurs and life here was completely different from what we know today. These gravitational waves, produced by a collision between two neutron stars, caused a series of changes. The planet's life witnessed the evolution and extinction of species, the emergence and disappearance of civilizations, and the development of instruments capable of measuring the slightest distortions in spacetime. With the detection of gravitational waves and light from the fusion of stars, astrophysicists recognized a distinct glow that indicated the presence of new heavy elements. Humanity witnessed the production of these elements from the ancient remnant of a luminous star, which amazed experts in cosmic cataclysms for the science and romance of this story. The discovery answered several long-standing questions in astrophysics while also raising new questions. Many scientists are excited about the new ability to detect gravitational waves and light from the same cosmic source, promising to help understand astrophysical explosions and element synthesis in a way that was previously impossible. Over the past few decades, several scientists have debated possible locations in the universe where the R process could occur. However, this question remains one of the biggest mysteries in nuclear astrophysics. Initially, many researchers believed that core-collapsed supernovae could host these processes. However, supernova simulations were unable to reproduce the necessary thermodynamic conditions and neutron richness. In 1974, James Lakemire and David Sherman suggested that decompression of neutron star matter could provide the ingredients for the R process. When a massive star runs out of nuclear fuel, its gravity causes the core to collapse. The force of the star's mass on the core compresses it to extremely high densities, causing electrons and protons to merge into neutrons, while the rest of the star is expelled in a supernova. The neutron star remains intact, a compact remnant containing the densest matter known in the universe. Neutron stars with more mass than a certain limit collapse further into black holes. However, it is still unknown exactly where this transition occurs and how soft these stars can be. The internal structure of neutron stars is an open question. They may contain mainly neutrons and a small fraction of protons within a crust of heavier nuclei on their surface. However, it is possible that their interiors are even stranger than imagined. Scientists suggest that the collision between a neutron star and a black hole could eject neutron-rich matter. However, in 1982, the most accepted theory involved the collision between two neutron stars. While some researchers focused on understanding how these collisions could synthesize new elements, others tried to predict what kind of light. Some theories suggested a connection between neutron star collisions and gamma-ray bursts, which are highly energetic explosions in space that emit a flash of gamma rays. These theories were based on the fact that the nuclei of the R process would be stable and undergo radioactive decay, heating the material around them and fueling an electromagnetic explosion that would carry the signatures of the produced elements. Despite intense theoretical development, there was little direct confirmation until recently, when a remarkable set of observations could come directly from the center of a neutron star merger. Now, scientists have the opportunity to closely study the processes that occurred during these collisions and further improve their theories about the formation of new elements in the universe. To understand the R process, experts from various disciplines will have to work together: observational astronomers studying both new and old stars, gravitational wave astronomers measuring distortions in spacetime, nuclear theorists building models of nuclear structures and matter within stars and neutrons, experimental nuclear physicists tracking the properties of unstable neutron-rich nuclei, and computational astrophysicists simulating events such as neutron star mergers, solving equations that take months to process on some of the world's largest computers.